Today we're going to go over tension problems and how to solve them using Newton's second law. So tension is just another force caused on an object due to it being suspended or pulled by a rope, cable, wire, something like that. As you can see here are two common examples. We have a block connected to another block on a table, or we have a pulley system as shown on the right. Um, Whenever you see wires, ropes, honestly, long lines on your paper, it's a tension problem. So let's get right into it. So this is just a basic problem to get you used to tension. A 10-kilogram mass hangs from a rope at rest, what is the tension in the rope? So first things first, the rope and mass is at rest. So this means that acceleration is 0. So as with any physics problem, let's first start off by drawing it. So I'm going to assume that it's hanging from a ceiling of some sort. We have a ceiling, a rope, and a mass, a 10-kilogram mass. All right, and that's it. So let's go to our free body diagrams. As always, free body diagrams are one of the first things you always do with every single type of problem because it'll tremendously help you. And if you do not do your FBD, free body diagram, you are more likely to make a mistake and it will hurt you. So please, please, please take the time to do it. Enough said, let's get right into it. So we have our element, we have our weight force being mg pointing downward, and we have our T for tension force pointing upwards. And remember to draw your coordinate system. So I'm going to draw y, positive y up, positive x to the right. And there is no acceleration in y or x direction, and there's only forces in the up and down, so in the y direction, so we can completely ignore x. So let's write our Newton's second law. So we have F is equal to ma, and I'm going to write in the y direction because that is the more interesting direction. A is 0 because it's at rest, so we have sum of forces is equal to 0. A sum of forces can be rewritten as positive t because t is pointing up, and up is the same direction as our positive y, minus mg minus again because it's pointing downward is equal to 0. So we can rewrite this as t is equal to mg. We know m is 10, we know g is 9.8, so we get tension is equal to 98 newtons of force. So what that means is the rope is, there's 98 newtons of force in the rope in order to hold the mass at rest. All right, so hopefully this kind of shows you how similar this is to any other Newton's second law problem. Let's get on to a slightly more difficult problem. This is the kind of problem you will see on an exam, most likely. We have a 6-kilogram block on a table and connected over a pulley to a hanging 4-kilogram mass. The kinetic friction coefficient of the table is 0.2. Find the acceleration of the system and tension in the rope. Now, if the kinetic friction coefficient, I have another video on my channel that goes about how to solve for friction with these types of problems. So if you have trouble, check out that video. I will briefly go over it in this video for this problem, but if you want more detail, please check that video out. All right, so first things first is let's draw it. So we have our little table. I'm just gonna do, it's a terrible table, guys, I'm sorry. We have, I'm gonna call this mass 1. This is gonna be the 6-kilogram one. And it's connected to a pulley with a 4-kilogram mass. I'm going to say this is mass 2. I'm going to put a pulley right there. A pulley just kind of tells you that, you can ignore friction in the pulley or whatever, but we can't ignore friction in the table. So I'm going to draw a little bit of a rough surface in the image to remind me there is friction. It's not a smooth surface. All right, let's get on to our free body diagrams. So one thing to note in this case is we have two masses. We have two systems, or two parts of a system. So I'm actually going to draw two free body diagrams, one for each mass, so that I can simplify this problem. Because otherwise, I can't draw one free body diagram for the entire thing. So for the first mass, I have our element. I have tension pulling the rope to the right. We know that there's friction in this problem because there's a kinetic friction coefficient. So I'm going to say friction force to the left. We have our weight force, which is M1G, and we have our normal force. Oh, this is tension. I don't know why that. All right, and always with your free body diagrams, make sure you have your coordinate system. So I'm going to have positive y to the top, positive x to the right. And it may seem redundant to write these coordinate systems, but just wait for a second. Later in this problem, you'll see why it's important. All right, so we're trying to find tension and acceleration, but we don't actually know friction force. Again, as mentioned earlier in my other video, when I talk about friction, we learned that friction force is equal to coefficient of friction times the normal force. Um, so let's solve for the normal force in for our this free body diagram. So we have sum of forces in the y direction because normal is in the y, is equal to mass 1 times g, sorry, mass 1 times a times acceleration. No, I'm sorry. I was right earlier. M1 times, no, I'm so sorry, guys. It's been a long day. M1 times A, but A is 0, AY is 0 because the mass is not accelerating up or down. So this whole system becomes 0, and we have positive N minus M1G because M1G is pointing downward, which is the negative Y direction, is equal to 0. So we have the normal force is equal to M1G, which is equal to 6 times 9.8, which is 58.8 newtons. So putting that back into here, we have friction force is equal to 0.2 times 58.8, and this is equal to 11.76 newtons. All right, so that is how we get our friction force. Now let's solve Newton's second law in the x direction. So sum of forces in the x is equal to mass 1 times acceleration in the x. This one, I'm not going to write acceleration in the x. I'm just going to write a because the acceleration on the x of this one, this block, is the same as the acceleration of y of this, of mass 2. So I'm just going to write it as a, just to help me know that they're the same. All right, so for the x direction, I said right is positive. So we have T minus friction is equal to M1A, and this is just T minus 11.76 is equal to 6A. And I'm going to underline this because this is going to be our first equation, right? Because we have tension and acceleration, something we are trying to solve for both for. All right, so we got all of that just from one free body diagram. Now let's go on to draw free body diagram number 2. So of this now. So we have our element, we have weight going down, so M2G, and then we have tension going up. That's it. And again, I'm writing tension as just T rather than TX, TY, or T1, T2, because the tension on the rope here is the same as the tension on the rope there. It's the same rope. The tension on either side of the rope has to be the same. Otherwise, the rope is broken, and it's not a tension problem anymore. So tension has to be the same. All right. So now let's solve for, put this into Newton's second law. We have, and for this one, before we do that, I'm gonna redraw my coordinate system. So I have positive x to the right, and I'm actually gonna have my positive y downwards. I'm having my positive y downwards for this system because I know that it is accelerating down. You can draw it as positive y to the top. However, you just have to be aware of all your negative signs. It isn't wrong. You can solve both ways and you'll get the same answer. But just be very careful with the signs. But for this case, just to show you something new, I'll have my coordinate system be like this. All right, now to Newton's second law. So we have sum of forces in the y direction is equal to m2a. We know it's accelerating because it's moving. Our forces are m2g, positive, because it's, again, down is positive, minus t is equal to m2a. And plugging in our numbers, we can get, this is 4 times 9.8 minus t is equal to 4 times a, which is just 39.2 minus t is equal to 4a. And this is our second equation that we can use. And now, using basic substitution, we can rearrange these problems to solve for t and a. So let's go ahead and do that. So I'm going to rewrite this equation first. So I'm going to say t is equal to 6a plus 11.76. I'm going to plug this into here. So I'll have 39.2 minus 6a plus 11.6 is equal to 4a. Now, through algebra, I'm not going to do it, but feel free to solve it on your own, see if you get the same answer. We get that acceleration is equal to 2.744 meters per second squared. So in the comment section, let me know if you got the right answer or something different. All right, now that we have our acceleration, we're going to plug this back into here. So we'll have t is equal to 6 times 2.744 plus 11.76. And from this, we can get that tension is 28.224 newtons. There you go. That is our final answer for this type of problem. Again, this is a very, very, very common problem. I have seen it on my Physics 1 exam in high school for AP. I've seen it in 2 different physics classes in college at Georgia Tech. This is a very, very common problem, so make sure you study this up. In the next video, I'm going to solve another quite difficult problem that is very common in exams. To give you a little bit of a sneak peek, it looks something like this, where we have more than one cable or rope, meaning we have more than one tension at various angles. This is a very common exam question for AP exams, for Physics 1 finals in college. So make sure you check that video out. But I hope now you have at least a basic understanding of tension problems using Newton's second law. Till next time.